All right, guys. We're back with another video. Apologize for the hiatus, but I was a little bit sick, and it wasn't coronavirus, but again, we're back with our next lecture. This is on 10.2. It's on the inverse of a Laplace transform, right? So we covered in 10.1 that what we're really looking to do is we're looking to take a differential equation, convert it into an alternate language, basically using Laplace transforms, solve it there, and then take the inverse of that to basically untranslate the answer. So, in order to do this, we'll need some required skills. First and foremost, I need my Laplace transform formulas. All right, the ones we learned from section 10.1. And we're going to need one more thing that we remember from one of our previous calculus classes. We're going to need partial fraction decomposition. Yay! I love partial fraction decomposition. Seriously. That's one of my absolute favorite things to do. It's fantastic. It's just, I'm very, very excited. But okay, we won't need this till much later, like maybe the very last example we do. Okay? So let's talk about how this is going to work. Well, predominantly we're going to do this by formula, right? What we have is we have this linear transformation, our Laplace transform, which is basically mapping some function in t, and it's giving us another function in s, right? And so the inverse for this, what I would really want, and this is the way we define it somewhat canonically, is that I say that the inverse Laplace transform of this function is equal to f of t, if and only if that this is the function that got me here, right? So what I can do is I can take the formulas that we had in section 10.1, and I can just write them backwards. Right, I can write them backwards. Okay, so let me get a chart of those on the right, and I want to leave off the polynomial one for last because that one doesn't go quite as cleanly. But if we remember, the inverse Laplace transform of 1 over s minus a. Well, let's see. What function gave me the Laplace transform of 1 over s minus a? Well, that was e to the at, right? And the inverse Laplace transform of s over s squared plus b squared, that's cosine bt. And the inverse Laplace transform of b over s squared plus b squared, sine bt. Okay. The polynomial, that's getting a little crooked. The polynomial one's a little bit different. Because there's some constants that we're going to want to sort of rearrange. Let me put the actual Laplace transform definition up here. What I have is that I have the Laplace transform of t to the n power is n factorial over s to the n plus 1. Okay. So let's see if we can't maybe use this to get an inverse Laplace transform formula. Take the inverse Laplace transform of both sides. Okay. And remember, I'm defining this as the inverse. So this is t to the n. And I know that this is a linear transformation. So remember, n is fixed, right? N is not a variable. N is fixed. So I know that n factorial is a scalar. It's some number. Let me go ahead and divide both sides by that. And I got t to the n over n factorial. is equal to the inverse. So this is this formula is not really designed as cleanly as we would like, and this happens periodically in mathematics when you have a formula. And so we call this relabeling, right? We call this relabeling. These three values are related, right? That's n, that's n, that's n plus 1. And I would really like a nice clean formula, something along the lines of the inverse Laplace transform of 1 over s to the n, right? Some nice clean formula. But notice, in order to get from here to here, I just have to tick this down by 1, right? Yeah? I have to move n plus 1 to n. I just tick it down by 1. And so what I'm going to do for this entire formula, I'm just going to take all the n's and replace them with n minus 1, right? And so that's going to give me s to the n. But on the left-hand side here, it's going to give me t to the n minus 1 over n minus 1 factorial, right? So not exactly the literally writing it opposite like we did for the other ones, but this gives us somewhat of a nicer version of this formula. Okay, the important thing here is my inverse, obviously it's a linear transformation, it's additive, it's scalar invariant, all the very nice things apply, right? I'll do a couple maybe real easy examples here before I get into some of the more fun versions. So maybe something like what's the inverse Laplace transform of 4 over s cubed? I'm pulling a problem out of your book, right? So what's the inverse Laplace transform of 4 over s cubed? Well, we just apply the formula, right? Okay, the 4 doesn't matter. Again, it's linear transformation. I've got s cubed, n here is 3. This is t to the 3 minus 1, that's 2 over 3 minus 1 factorial, that's 2 factorial. This turns out to be 2t squared. Easy peasy, right? Okay, maybe something that requires maybe a little bit of effort. Okay, how about 2s plus 1 over s squared plus 16. So this kind of looks like these two, right? Yeah, that's s squared plus b squared, where b is 4. The difference here is that it's either s or b, it's not both. And so what I can do is I can actually just split this fraction. Okay? So I can rewrite this as 2 times the inverse Laplace transform of s over s squared plus 16 plus, I'm going to leave some space here for a reason, the inverse Laplace transform of 1 over s squared plus 16, right? And so again, I'm just breaking apart this into 2s plus 1, the same denominators, and so I factor out the 2, I've got 2s plus 1 over s squared plus 16. This looks ready to go, doesn't it? Yeah? This is quite literally s over s squared plus 4 squared. That's exactly my cosine formula. This is cosine 4t. This one, not so much, right? This is supposed to be b over s squared plus b squared. And if this is 16, b has to be 4, right? So I really need this 1 to be a 4. And I can accomplish that by, well, what I'm going to do is I'm just going to multiply a 4 into this numerator, and I'll put a 1/4 out here, right? 4 times 1/4 is 1. Okay, that'll fix my fraction. This is 4 over s squared plus 4 squared. That's fantastic. And I get 1/4 sine 4t. Easy as pie, right? Okay. And I know what you're thinking. You're thinking, you promised me some partial fraction decomposition, and as of yet, you have not delivered. Okay, let's do some partial fraction decomposition. Wait, quick, first and foremost, on page, hold on, 681 of your book, page 681, they've got the full chart of all the formulas that they have, all the inverse formulas and Laplace transform formulas. It's a very good chart. It's all located in one spot. Make sure that you pay attention to those things. You'll need to know those. Again, you can't do these things unless you have it memorized. It's like trying to learn German, but you don't know any of the German words, right? Okay, so let's do one that requires some partial fraction decomposition. In the problems we work that have LaPlace transforms, the following might come up, okay? So you might have to untranslate something that looks like the following, that looks like s minus 2. Okay. And this is a problem, right? Because if the denominator was s minus 2, we would know how to handle this, right? If the denominator was s squared plus 1, we would know how to handle it. And the problem is, it's neither of those things, right? They're combined. Well, it would be really nice if this thing was written as maybe something over s minus 2 plus something else over s squared plus 1. And now we see where the partial fraction decomposition comes in, right? That's exactly what I want to do here, yeah? All right, so the first bit of scratch work here, before I can even start to untranslate this, as I need to rewrite this, of course, this has a linear denominator, okay? So my numerator is constant. This has an irreducible quadratic of multiplicity 1. So my numerator is linear. In general, when you're doing partial fraction decomposition, please remember that, and you might need to replay this part of the video. Let me write it down. Hold on. The numerator should be 1 degree less than the factor creating the denominator. I should be very, very careful. So if hypothetically speaking, in the middle of a partial fraction decomposition, you had something like s minus 3 cubed, the numerator for this is still constant, right? It's going to be, I don't know, c. Okay? It's not, this is cubic. This is not going to be an arbitrary quadratic, because note that the factor here is s minus 3. You just happen to have 3 copies of it, right? That factor is still linear. So the numerator has to be 1 degree less than the factor, not 1 degree less than the denominator as a whole. Does that make sense? Right? So just bear that in mind in case you ever get a situation where you've got factors that have multiplicity larger than 1. And we're going to have those once we get to 10.4, I believe. Okay? All right, so let's go ahead and do this partial fraction decomposition so I can get my, my separate fractions here. What I know then is that these two things are equal, of course. So multiplying through by my common denominator here gives me the statement that 2s plus 3 is equal to a times s squared plus 1 plus bs times s minus 2 plus c times s minus 2. Now you might notice I do this a little bit differently than most people do. This numerator would be multiplied times s minus 2. If you multiply times this denominator, the s squared plus 1s would cancel. And most people write that together. I'm going to write it separately because I want one single term here for each one of my unknowns a, b, and c. Right? It's a little bit more organized. And I'm not going to multiply all this crap together. Right? Ideally, I would like not to do that. And for small partial fraction decompositions, here's the quickest way to do it. First, do all of your cheater values, right? Look at this denominator. Figure out if there are any nice real values that will make this 0. And clearly there is one. It's s equals 2, right? S equals 2 will make that 0. Now remember that this equation is true, and it's true for every possible value of s, so it must be true if s is 2. So I just plug in s is 2. Well, on the left-hand side, you plug in s is 2, and you get 7. 2 times 2 plus 3. And on the right-hand side, you get a times 2 squared plus 1, that's 5a. But look at what happens here. 2 minus 2 is 0. That whole term goes to 0. 2 minus 2 is 0, whole term goes to 0. This is the entire equation when you plug in 2, and so therefore a is 7/5. All right, pretty easy. Unfortunately, I can't do the same thing for b and c because this doesn't have any real roots, right? Technically speaking, you could plug in the roots of this are I and negative I, but if you do that, you're going to end up with a system anyway, so maybe there's an easier way to do it. And what I'd like for you to notice is, notice that b has an s attached to it and c does not. So consider the following, that the right-hand side is a quadratic, yes? The largest degree term you'll have here are s squared terms, right? So let's look at all the s squared terms. On the left-hand side, I have 0s squared, right? I mean, I know I didn't write it, but there are no s squareds. So on the left-hand side, I've got 0s squared. Let's look at the right-hand side. On the right-hand side, if I were to multiply all this crap out, and I don't want to do that because maybe this ends up being large, right? But if I were to multiply it out, I can track where the s squared terms are going to come from. I've got a times s squared, that's as squared. I've got bs times s, that's an s squared term. C can't make an s squared term, right? I've got c times s times negative 2. C can't make an s squared term. So there are no more, this is it. Well, if these are all of the s squared terms, then this must be equal, and so therefore 0 must be a plus b, but I know what a is. A is 7/5. So b must be negative 7/5, because b plus a must be 0. All right. Well, let's see if we can't do some same logic here. A lot of teachers, whenever they teach partial fraction decomposition, they teach you to plug in 0. Yeah, sure, that would work, but why does it work? It works for the same reason this did, okay? Notice that b has an s attached to it, which means b cannot possibly participate in constant terms, okay? Let's look at my constant terms, okay? On the left-hand side, my constant term is a 3. And on the right-hand side, I've got a times 1, that's a constant term. Notice that b cannot create a constant term. bs times s, that's bs squared, bs times 2, negative 2bs. Neither of those are constants, but c can. C times negative 2, so I've got minus 2c. It's pretty nice, right? And again, I know what a is. A is 7/5. So we have 3 is equal to 7/5 minus 2c. Subtract this over, you've got 8/5 equals negative 2c, and therefore negative 4/5 is equal to c. Fantastic, right? Okay, so all of this gives me my decomposition, and having done this, this is just the scratch work, now I can actually do my inverse Laplace transform. All right, so let me recopy. I'm gonna have to erase this, so let me recopy these up here. So a, that was 7/5. Let me write that up here. 7/5, and we have bs plus c. Oh, erase, 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 erase. Okay, so I've got negative 7/5 s minus 4/5. Okay. All right, let's see what we've got. All right, so instead of doing the inverse Laplace transform on this thing, which I don't really know how to do, I'm going to do the inverse Laplace transform on this version, because I know that my Laplace transform is additive and it's scalar invariant, right? It's a linear transformation. So let's see if I can do that. Okay, so let's take the inverse Laplace transform of 7/5 over s minus 2 plus the inverse Laplace transform of negative 7/5 s minus 4/5 all over s squared plus 1. Okay. Well, I can separate these the same way I did in the previous example I did. Again, it's scalar invariant. I can separate these fractions. I can pull the scalars out. And that allows me to rewrite these very nicely. It allows me to rewrite these things as 7/5 times the inverse Laplace transform of 1 over s minus 2, very nice, minus 7/5 times the inverse Laplace transform of s over s squared plus 1, again very nice, minus 4/5 times the inverse Laplace transform of 1 over s squared plus 1. Again, multiplying these things back in, I would get negative 7/5 s minus 4/5. That's exactly the numerator I had. And then each of these things inverts very nicely. This is the definition, 1 over s minus a. This is e to the at. So I have 7/5 e to the 2t. Okay, so minus 7/5 here. This is s over s squared plus b squared. This is cosine, where b is 1. This is cosine 1t. Here I have the Laplace transform of sine, b over s squared plus b squared, where b is 1. So minus 4/5 sine bt. Fantastic. Okay, so the inverse Laplace transform of f. All right, not terrible, right? Again, there's a lot of arithmetic to get in here, maybe a lot of algebra, but overall, very easy as pie. This is somewhat of a short lecture video today. This will get slightly more complicated once we start getting into some of the more complicated Laplace transform rules, like the first shifting theorem, the second shifting theorem. But for right now, your goal at the end of this section is to be able to put these nice simple functions into and out of Laplace transforms somewhat quickly and efficiently. Okay? All right, guys. Again, homework has already been posted. Please make sure you're doing that stuff and keeping up with it. Good luck.